Hello, everyone. Tonight, we're going to build something impossible. Not in a loud, heroic way, in a quiet way, patient, methodical, like stacking stones beside a cold river, one careful step at a time. We're going to imagine a human colony on Mars, a real colony, not a flag and a footprint. Not a short visit, a place where people live through winters and dust storms, a place that keeps going when ships stop arriving, a place that makes its own air, its own water, its own repairs, and eventually its own future. And as we build it, we'll also understand why it's so difficult, because Mars is not merely far away. Mars is a different kind of world, a world that looks familiar in photographs: rust-red plains, pale skies, craters like dry lakes, yet behaves like an alien machine built to challenge biology. Mars is beautiful, and Mars is harsh. So this will be a story with two threads. One thread is practical, what we would actually have to do to build a colony. The other thread is honest, why each step is harder than it seems. We'll follow a small group of settlers, not named heroes, not movie characters, just steady people who work in a steady rhythm. Engineers, biologists, doctors, geologists, electricians, farmers who will become farmers again, but under a different sky. And you, listening tonight, can simply drift along with them. No pressure to remember every detail, just a calm sense of how the puzzle fits together. Because a Mars colony is not one invention, it's 1,000 small inventions stacked into a fragile chain. And the art is keeping the chain unbroken. Take a slow breath. Imagine the sound of a ventilator fan, the soft click of valves, the faint hum of power electronics. This is the soundscape of survival on Mars. Let's begin. The first rule: Mars is not almost Earth. Before the first habitat lands, before the first greenhouse glows, before the first boot touches the dust, there is a simple truth. On Mars, the environment does not support human life for even a few minutes without technology. Not because Mars is dramatic, because Mars is missing the quiet background conditions Earth provides for free. On Earth, you breathe without thinking. On Mars, breathing is an industrial process. On Earth, liquid water can sit in a glass. On Mars, water is a resource you must trap, melt, purify, and protect from freezing or boiling away. On Earth, the atmosphere blocks most harmful radiation. On Mars, radiation arrives like invisible weather. On Earth, you can walk outside with a coat. On Mars, outside is a vacuum-like cold with a near non-existent atmosphere, dust, and an ever-present risk that a small leak could become a fatal one. Mars gives you almost nothing for free, which means a colony is essentially a life support system that people live inside, a village made of pressure vessels, a town built from airlocks, a society wrapped in plastic, metal, regolith, and redundancy. And that is why it's hard, because Earth is generous and Mars is not. Now, the good news is that Mars does offer some helpful things. It has day and night, not exactly Earth length, but close. A Martian day, called a sol, is about 24 hours and 39 minutes. Mars has gravity about 38% of Earth's, which is low, but not zero. Mars has water ice in the soil and in the polar regions. Mars has carbon dioxide in the atmosphere, which is thin but abundant enough to harvest. Mars has sunlight less than Earth, but enough to matter. Mars has raw materials, iron-rich regolith, silicates, sulfates, and plenty of chemical potential. Mars is difficult, but it is not nothing. So the question becomes, how do we convert not nothing into a living place? We start the way humans always start, by bringing a small bubble of Earth with us. Chapter 1. The first landing and the first bubble of air. The first cargo mission arrives before the people. It has to. Mars is too far for we'll figure it out when we get there. Launch windows open roughly every 26 months. If you forget a critical part, you can't run to the store. So the colony begins as freight. Uncrewed landers touch down first, kicking up dust and silence. They carry habitat modules, pressure shells that can become living space, power systems, solar arrays, batteries, perhaps a small nuclear reactor, water extraction equipment, heaters, drills, pumps, filters, life support units, oxygen generation, carbon dioxide scrubbers, humidity control, tools and spares, valves, seals, sensors, wiring, lubricants, robots to unload, drag, assemble, and prepare, medical gear, far more than a normal expedition. A seed bank and growth systems, lights, hydroponic hardware, nutrient salts, communication equipment, a high-gain antenna, relay stations, local network nodes. And the cargo has another job. It has to prove the landing site is not lying. Mars can be treacherous at small scales. A flat patch in an orbital image might hide rocks. A region might have softer soil than expected. Dust might accumulate differently than models predicted. So the first machines do something gentle and important. They measure, they map, they test the ground, they deploy weather stations, they sample regolith, they look for shallow ice, they watch the dust, they listen to the wind. And slowly, the first bubble of infrastructure appears. A cluster of modules, cables uncoiling like vines, solar panels tilting toward the pale Sunday, a small line of lights marking a safe approach path for later landings. If you could see it from above, it would look like a tiny mechanical campfire, not bright, but purposeful. Then, when the systems are stable, the people launch. During transit, they live in another artificial bubble, one that must manage radiation and microgravity. That's an entire story of its own. But tonight, we focus on Mars. Months later, the crew arrives. The landing is violent and quiet at once. Violent in physics, heat, deceleration, engines. Quiet in sound, the thin Martian air carries little. When the hatch opens, there is no breath of fresh air. There is only the procedure, pressure checks, suit checks, airlock cycle, a step onto dust that has waited billions of years, and then back inside. Because on Mars, going outside is a task, not a default. The settlers move into the habitat. They begin the first true work of colonization. They turn supplies into a system, Because a pile of equipment is not a colony. A colony is a loop: air loop, water loop, power loop, food loop, waste loop, maintenance loop, and eventually, social loop. Let's build those loops one by one. Chapter 2: Air making oxygen, removing carbon dioxide, holding pressure. How? On Earth, air is a background gift. On Mars, air is inventory. The habitat must maintain pressure often similar to Earth's sea level or somewhat lower, depending on design. But pressure is not only comfort. Pressure affects boiling points, gas exchange in lungs, fire behavior, structural loads, and how dangerous a small leak becomes. The first air system has 3 essential jobs: provide oxygen, remove carbon dioxide, control humidity, and trace contaminants. Oxygen, what you can bring and what you must make. At first, the settlers bring oxygen: compressed tanks, chemical oxygen generators, reserves. But for a colony, imported oxygen is not enough. It's too heavy, too expensive, too fragile. So a colony must generate oxygen locally. Mars offers 2 main oxygen sources: water split into hydrogen and oxygen, carbon dioxide split into carbon and oxygen, or processed via chemical cycles. Splitting water by electrolysis is conceptually simple. You pass electricity through water, you get oxygen and hydrogen. But the simplicity hides the real complexity. Where does the water come from? How pure is it? How do you prevent freezing in pipes? How do you store hydrogen safely? How do you keep electrolyzers reliable for years? Some missions also generate oxygen from carbon dioxide using solid oxide electrolysis, like an advanced high-temperature device that takes in CO2 and outputs O2 and CO. This is elegant because Mars's atmosphere is mostly CO2. But again, high temperatures, brittle materials, dust contamination, maintenance. A colony uses redundancy, multiple methods. Because air is not optional. Carbon dioxide removal, the quiet battle. In a closed habitat, carbon dioxide rises quickly. CO2 is not poisonous in the dramatic way movies imply, but elevated CO2 causes headaches, fatigue, and impaired thinking, exactly what you don't want in a high-risk environment. So the colony uses scrubbers. Some use chemical absorbers. Some use regenerable systems, molecular sieves, pressure swing adsorption, or other methods that capture CO2 and release it later for disposal or reuse. Reuse matters. CO2 is not just waste. It's feedstock. Plants like CO2. Chemical systems use CO2 to make fuels and plastics. A colony learns to see waste as raw material. That's the mental shift. But to do that, the system must be stable, which leads to a truth the settlers learn early. On Mars, stability is a form of wealth. If your air system is stable, you can think. If it's unstable, everything becomes emergency, pressure, and leaks. The constant paranoia that becomes routine. Habitats leak. Everything leaks. Valves seep. Seals age. Materials shrink and expand with temperature. Micrometeoroids can puncture outer layers. And Mars, dust fine, abrasive, electrostatically clingy, works its way into joints and mechanisms. So the colony is built with layers: inner pressure shell, micrometeoroid protection, thermal insulation, external shielding, often regolith, piled over habitats, leak detection sensors, compartmentalization, bulkheads and doors, so a leak doesn't doom everyone. Leaks are not dramatic most days. They are slow. The habitat compensates. Then a sensor pings. A technician follows the sound with an ultrasonic leak detector. They patch, they log, they move on. This is what life becomes: calm vigilance. End quote. Now that we can breathe, we need water. And water on Mars is both a resource and a riddle. Chapter 3. Water: finding it, melting it, cleaning it, never letting it go. Water is life. Water is oxygen. Water is hygiene. Water is agriculture. Water is cooling. Water is chemistry. And on Mars, water is also a kind of currency. The more you can harvest locally, the less you must ship from Earth. Mars has water, but often as ice mixed into soil or as subsurface deposits. The colony chooses a site partly for water access. A place with shallow ice is a place with a future. Istikhraj, or rather extraction, turning ice into usable water. A water system typically includes drills or excavators to collect icy regolith, heating units to melt or sublimate ice, condensers and cold traps, filters to remove dust and salts, storage tanks with thermal control, recycling systems that reclaim water from humidity, urine, and wastewater. Recycling is not a luxury, it is survival. On the International Space Station, water is recycled extensively. A Mars colony pushes this to near maximum because replacing water by shipping it is brutally expensive. And because the supply chain is slow, if a part fails, you might wait years for a new one unless you can manufacture it, which we'll get to. But even with ice available, water is hard. Mars is cold. Pipes freeze. Valves stick. Ice can be mixed with perchlorates and other salts that complicate purification. Water extracted from regolith might contain dust so fine it behaves like smoke. So the colony becomes careful. Water processing runs quietly in the background. Sensors watch conductivity, pH, microbial content. Filters are swapped. Membranes are cleaned. And every liter is tracked. Not because people are miserly, because every liter is labor, power, and risk. The psychological shift. Water is a loop. On Earth, you flush and forget. On Mars, you flush and remember. Because that water will come back to you, cleaned, reclaimed. A loop. The settlers adapt to it. At first, they think about it constantly. Then it becomes normal. Human beings can normalize almost anything if it keeps them alive. Now we have air and water. But air and water require power. Power is the heartbeat. Without power, everything becomes cold, dark, and silent. Chapter 4. Power: the colony's heartbeat and the dust that tries to stop it. Mars gives you sunlight, but weaker than Earth's. And Mars gives you dust, Dust that can cover panels. Dust that can darken the sky for weeks. Dust that can infiltrate mechanisms and coat radiators. So a Mars colony needs power that is reliable, redundant, maintainable, scalable. Solar power, abundant, until it isn't. Solar arrays are attractive. They are mature technology. They can be deployed in large fields. They scale reasonably, add more panels, get more power, but Mars sunlight is weaker and dust is relentless. So solar power comes with chores, regular cleaning, robots sweeping panels, electrostatic dust removal systems, panel tilting to shed dust, and planning for the worst, global or regional dust storms that reduce sunlight dramatically. During big storms, power may drop. The colony must ration. Known essential systems shut down. Heating becomes critical. Batteries carry the night, but not weeks of darkness. So, solar alone is risky for a serious colony. Nuclear power, steady, with its own complexities. A small nuclear reactor provides stable baseline power. It doesn't care about dust storms. It doesn't care about night. It provides heat as well as electricity, which can be useful. But nuclear systems are heavy, politically complex, and require careful safety design. They also require maintenance plans and high reliability. A colony might use nuclear as the base and solar as the supplement. That combination is calming. Solar for expansion and extra energy. Nuclear for stability. Energy storage. Batteries, chemical storage, and how long can you coast? Even with nuclear, storage matters. Batteries handle peak demand and provide smoothing. Chemical storage, like hydrogen produced by electrolysis, can store energy later used in fuel cells. Thermal storage can hold heat through the night. The colony designs for coasting time. If something fails, how long can the system run while people fix it? On Earth, your coast time is infinite because air and pressure are free. On Mars, coast time is a number in a spreadsheet, and it must be generous. This is why Mars is hard. Mars demands you plan for failure like it's weather, because it is. Now, we have a powered bubble with air and water. We can survive, but survive is not colony. To become a colony, you need food. And food is not just calories. Food is biology, psychology, culture, and time. Chapter 5. Food farming under a rust-colored sky. The first settlers bring food, dry meals, freeze-dried ingredients, stored fats, vitamins, enough for months, maybe a year. But shipped food has limits. It's heavy. It degrades over time. It provides little variety, and it locks the colony into dependence. So farming begins early. At first, not as romance, as engineering. Greenhouses, not glass, but controlled ecosystems. A Mars greenhouse is not a simple room with sunlight. It is an environmental machine. It controls temperature, humidity, CO2 levels, light intensity and spectrum, nutrients, microbial contamination, pollination strategy, water recycling. Some crops grow in hydroponic systems, roots in nutrient solution. Some in aeroponics, roots misted with nutrients. some perhaps in treated regolith, but Martian soil contains perchlorates and lacks organic structure, so it needs processing. The colony begins with hardy, high-yield crops, leafy greens, fast growth, high nutrition, potatoes or similar tubers, calorie density, legumes, protein and nitrogen cycling, herbs, small but psychologically powerful. They also grow algae or microbial protein sources because those can be efficient. But farming on Mars has a hidden enemy: time. Plants take time. If a crop fails, you can't replace it overnight. If disease enters the system, it can spread in the enclosed environment. If lighting fails, growth slows. So agriculture demands redundancy too. Multiple grow rooms, isolated, seed reserves, backup nutrient stocks, pest control methods suited to enclosed spaces. Why Mars farming is hard. Biology hates surprises. On Earth, agriculture is stabilized by large ecosystems, abundant air, and the ability to start over. On Mars, you're farming inside your life support. The greenhouse is not separate from survival. It is part of the survival loop. Plants also interact with human life support in complex ways. They produce oxygen, but not enough for full human needs unless you devote enormous area to crops. They absorb CO2, which helps, but they also emit volatile organic compounds and require careful humidity control. The colony learns that plants are wonderful, but they are not magical. You can't just put a tomato in a pot and call it a colony. You must engineer an ecosystem, and ecosystems are delicate. Yet when the first harvest comes, something changes. Not in the power system, in the people. They taste something fresh. They smell leaves. They watch something alive, growing on another planet. And for a moment, Mars feels less like a machine and more like a place. Still hard, but a place. Now we can breathe, drink, eat, and power our systems. We are alive, but we're not safe because Mars has hazards that don't care about our competence. Radiation, dust, cold, isolation, low gravity, and the simple fact that rescue is not quick. Let's talk about why Mars is so difficult as a home. Chapter 6. Why building a colony on Mars is so hard. A Mars colony is hard for one overarching reason. You are trying to run a small piece of Earth's life support systems continuously in a place that does not want them to run. But let's turn that into specific difficulties. 1. The atmosphere is thin, mostly CO2, and offers almost no pressure. Mars's atmospheric pressure is less than 1% of Earth's at sea level. This means humans cannot breathe it. Liquid water is unstable at typical surface conditions. You cannot rely on atmospheric pressure for anything. Habitats must be strong pressure vessels. Airlocks and suits are mandatory. On Earth, pressure is free. On Mars, pressure is infrastructure. 2. Radiation, the invisible weather that accumulates. Mars lacks a strong global magnetic field like Earth's. Its atmosphere is too thin to provide robust shielding. So cosmic rays and solar energetic particles reach the surface more easily. This increases cancer risk and can damage electronics. A colony deals with this by using shielding, cover habitats with regolith, build partially underground, use water tanks as shielding walls, design storm shelters for solar particle events. But shielding adds mass and complexity. Digging adds time and machinery, and radiation never stops being part of the background. It's like living under a sky that leaks, not always dramatically, but always. 3. Dust. Abrasive, clingy, and everywhere. Martian dust is fine, electrostatic, abrasive. It can wear down seals, clog filters, reduce solar power output, contaminate mechanical joints, irritate lungs if it enters habitats, carry perchlorate salts that complicate handling. Dust storms can reduce sunlight for long periods. Even without storms, dust is a daily maintenance task. On Mars, housekeeping is survival engineering. 4. Cold, the constant energy cost. Mars is cold, not uniformly, but enough that maintaining comfortable indoor temperatures requires continuous heating. That heating is power. Power is life. So thermal management is always present. Insulation, heat exchangers, radiators that must avoid dust accumulation, waste heat reuse from reactors or machinery. 5. Distance and delay. No quick help, no real-time control. Mars is far. Communication delay ranges from minutes to tens of minutes one way, depending on orbital positions. This means no real-time conversations with Earth, no joystick controlling robots from Earth, no instant emergency support. The colony must be autonomous, technically and socially. Distance also means supply delays. If something breaks and you don't have the spare, you might be forced to improvise with what you have. Which brings us to the next difficulty. 6. Maintenance. Everything becomes a life-critical device. On Earth, if your dishwasher breaks, you wash by hand. On Mars, if your CO2 scrubber breaks, you have a countdown. This changes how you design everything. Redundancy, multiple units, modularity, parts you can swap, repairability, tools, access panels, documentation, monitoring, sensors everywhere, training. Everyone must understand systems at least somewhat. Mars does not allow sloppy engineering, and it does not allow casual maintenance. 7. Human bodies. Low gravity is not fun. It's a medical unknown. Mars gravity is 0, 38 G. We do not yet know the full long-term effects of living for years in that gravity. We suspect bone density loss might continue, though perhaps less than in microgravity. Muscle atrophy could occur without exercise. Cardiovascular changes may persist. Vision changes might happen. Pregnancy and child development in low gravity are uncertain. A colony can exercise. It can use centrifuges for partial artificial gravity, perhaps. But it can't change Mars' gravity easily. So, the biology question remains one of the biggest unknowns. And unknowns make planning hard. 8. Psychology, isolation, confinement, and the pressure of consequence. Humans are adaptable, but not invincible. Mars will test group dynamics, conflict resolution, mental health support, the ability to handle monotony, the ability to handle chronic risk. You can't take a walk in a forest. You can't sit outside in the rain. Nature, in the earth sense, is absent. So the colony must create psychological nature, lighting that mimics day cycles, green spaces, private spaces, rituals, art, music, quietly, and community structure, purposeful schedules that avoid chaos. A Mars colony is part engineering, part sociology, and both must work. Now, knowing these difficulties, how do we proceed? We proceed with a plan that treats the colony like a living organism. It needs organs. It needs circulation. It needs redundancy. It needs growth. Let's build the colony in phases. Chapter 7. The phases of a Mars colony, from outpost to city. Phase 1. The outpost, don't die, learn everything. The first phase is small, maybe a dozen people. The goal is not comfort. The goal is stability and learning. They focus on establishing reliable power, setting up water extraction, closing life support loops as much as possible, testing construction methods, developing local repair capability, building a local map of hazards and resources. They live in connected modules, covered with regolith for shielding. They build a storm shelter. They create a maintenance shop. They set up a small greenhouse. They log everything, every pump cycle, every filter change, every dust accumulation rate. Mars is data. In phase 1, the colony is an experiment that people live inside. Phase 2, the settlement. Make it cheaper to live here than to ship life here. In phase 2, the population grows, perhaps a few dozen to 100. Now the goal shifts, not just survival, but local production. The colony starts making things. It increases agriculture. It builds larger habitats. It establishes a small factory for plastics and composites. Metalworking capability, perhaps using imported machines and local regolith-derived feedstock. A more robust medical bay. A redundancy layer for every critical system. Phase 2 is about reducing dependence. Because dependence is fragility. Phase 3. The colony. Build the loops that make children possible. A true colony implies multi-year continuity and the possibility of families. This is the hardest threshold because children mean long-term health in Mars, gravity, education systems, emotional stability, larger food production, more space per person, more robust governance, more robust medical capability. In phase 3, the colony becomes a society rather than a mission, and the society must still be an engineering project. That tension between human needs and machine needs is one of the deepest challenges. Phase 4. The city Mars industry and Mars culture. A Mars city would require large-scale construction, likely using local materials, industrial-scale power, robust transportation between sites, deep recycling infrastructure, a mature economy, and governance structure. This is not just hard, it is generational. And it requires a level of reliability that exceeds what we've ever built in space so far. But we can still tell the story calmly because each step is made of smaller steps. Now, Let's talk about the practical building methods. If you want to live on Mars, you must build on Mars, which means using Martian materials. Chapter 8. Building materials on Mars. Homes made from dust and stone. Shipping bricks from Earth is not a plan, so the colony uses what Mars offers. Regolith, the dust and rock fragments that cover the surface. Mars regolith can be processed in several ways. Sintering, heating regolith until particles fuse, forming solid blocks. Sulfur concrete. Using sulfur as a binder, Mars has sulfur compounds. Geopolymers, chemical binders made from silicates. Bricks formed by compression and heating. 3D printing using regolith-derived feedstock. Each method has advantages and difficulties. Sintering needs power and heat. Sulfur concrete behaves differently with temperature cycles. Geopolymers require water and chemistry control. 3D printing requires reliable machinery and consistent feedstock. And Mars adds a challenge. Earth doesn't. Thermal cycling. Materials expand and contract with temperature swings. Seals and joints must survive repeated stress. So construction is not just make a wall. It is make a wall that remains sealed for years in a harsh environment. Underground habitats, the calm solution with hard logistics. The easiest way to shield from radiation and temperature swings is to go underground. Lava tubes may exist on Mars' natural tunnels from ancient volcanism. If accessible, they could provide large protected volumes. But living in a cave requires access routes, sealing systems, air circulation, structural stability assessment, dust management, lighting, and psychological design. If lava tubes are not practical, the colony can dig trenches and cover habitats. Digging is heavy work, but robots help. Mars colonization is, in many ways, robot colonization first. Humans arrive to manage, adapt, and grow. Now, building structures is one thing, but the colony also needs mobility, rovers, transport, and logistics. Because a colony that can't move is a colony that can't expand. Chapter 9. Mobility and Logistics. The roads you can't pave. Mars does not have roads. It has terrain, rocks, dust drifts, slopes, craters, and the colony must move. People in pressurized rovers. Equipment for construction. Ice and regolith for processing. Replacement parts between outposts. Mobility on Mars is hard because wheels wear down in abrasive dust. Temperature affects batteries and materials. Dust can obscure sensors. Navigation must be reliable with limited external support. Rescue is difficult if a vehicle fails. So the colony uses layers of mobility. Small, unpressurized rovers for short tasks near habitats. Pressurized rovers for longer trips with airlocks and redundancy. Cargo haulers, often robotic, moving slowly but reliably. Drones are limited by thin air, but small rotorcraft can work at certain scales, though with constraints. Logistics becomes a science. Routes are mapped. Safe points are established. Emergency shelters are placed like islands, because on Mars, a long trip is not just distance, it is exposure. Now we come to one of the most important practical ideas for a sustainable colony: in situ resource utilization, often shortened to ISRU. A colony must make things from Mars. Let's talk about the biggest ISRU target of all: fuel. Chapter 10. Making fuel on Mars. The chemistry that enables return and growth. A Mars colony needs propellant for return trips to orbit, cargo vehicle operations in some architectures, emergency missions, potentially surface vehicles if using chemical energy storage, industrial chemistry feedstocks. The most discussed option is making methane and oxygen. Why methane? Because it can be synthesized from CO2 and hydrogen. Mars gives you CO2 from the atmosphere. Hydrogen comes from water. A common pathway is the Sabatier reaction, which combines CO2 and hydrogen to produce methane and water. And then you can recycle water back into electrolysis to get more hydrogen and oxygen. The specifics can vary, but the concept is elegant. Harvest CO2 from the atmosphere. Extract water from ice. Electrolyze water for hydrogen and oxygen. Combine hydrogen with CO2 to make methane. Store methane and oxygen as fuel. This creates a powerful loop, but again, the loop hides complexity. Compressing thin Martian air to obtain CO2 takes power. Electrolysis equipment must run reliably. Cryogenic storage is difficult in a dusty, thermally cycling environment. Leaks and contamination are dangerous. The system must be monitored constantly. Fuel production is one of the reasons Mars colonization is hard, but possible. Hard because the machinery must be robust. Possible because the chemistry is real. Now, a colony with fuel can support more missions, more cargo, more growth. But growth requires something more subtle than fuel. It requires parts, and parts require manufacturing. Chapter 11. Manufacturing and Repair. The difference between a camp and a colony. The settlers quickly learn that the most valuable machine is not the greenhouse, not the rover, not even the reactor. It is the workshop, the place where broken objects become working objects again. Because shipping spares for every possible failure is impossible. So the colony builds manufacturing capability in layers. Layer 1, basic fabrication. Cutting, drilling, milling, welding, 3D printing plastics. Simple electronics repair. Seal and gasket production. Layer 2, advanced fabrication. Metal, 3D printing, composite fabrication. Precision machining, circuit board manufacturing, very hard, but perhaps partial capability. Sensor calibration equipment. Layer 3, industrial capability. Istikhraj ores, refining metals, iron, aluminum, possibly others. Chemical production, plastics, solvents, lubricants, glass and ceramics from regolith. Standardized parts production. The deeper you go, the closer you get to a true colony. But the deeper you go, the more you need power, skilled labor, complex supply chains, quality control, safety systems. Manufacturing is a web. On Earth, you don't see the web. On Mars, you live inside it, and quality control becomes life-critical. A faulty seal is not an inconvenience. It's a hazard. So every part is tested. Every batch is tracked. The colony develops a culture of carefulness, not fear, care. Now, with food, air, water, power, fuel, and manufacturing, you might think the colony is stable. But stability is not just technical, it's medical. Let's talk about health on Mars. Chapter 12, Medicine on Mars, Treating the Body when Earth is Far Away. A Mars colony must be able to handle trauma, falls, equipment accidents, suit incidents, illness, infections, though limited by isolation, but still possible. Dental emergencies, surprisingly common and very serious if untreated. Mental health, anxiety, depression, conflict, chronic conditions, people age, even on Mars. Radiation exposure concerns over time. The medical bay must include surgical capability, limited but real, diagnostic imaging, portable ultrasound, perhaps compact scanners, a pharmacy with long shelf life medication, sterilization equipment, telemedicine support with time delay, training for non-doctor crew in medical procedures. Why is Mars medicine hard? Because the colony can't easily evacuate. In Antarctica, evacuation might be difficult, but it exists. On Mars, evacuation is a mission. And missions require fuel, vehicles, orbital mechanics, and time. So medical autonomy is non-negotiable. And yet, medical autonomy is expensive in mass, equipment, training, and emotional load. This is another reason Mars colonization is hard. You must pack an entire small hospital into a tin can and keep it running for years. Now, the most profound medical unknown is long-term, low gravity and reproduction. We don't have answers yet. A colony might delay having children until more is known, or it might use rotating habitats to provide higher gravity for certain life stages, or it might accept risk. But risk acceptance is a moral choice, not just an engineering choice, which brings us to governance. Because a colony is also a political entity, whether it wants to be or not. Chapter 13, Governance. Who decides when decisions matter most? In the first phase, the colony is a mission. A hierarchy exists. Roles are defined. Emergency authority is clear. But as the colony grows, governance becomes more complex. People argue. People disagree. People have different risk tolerances, different cultural backgrounds, different ideas about fairness. And because the environment is unforgiving, governance must be calm and functional. A Mars colony needs clear safety rules, transparent resource accounting, conflict resolution processes, work schedules that prevent burnout, decision systems for emergencies, long-term planning systems for growth. It also needs a legal relationship with Earth, at least initially, because shipments, funding, and mission control will be Earth-based for a long time. But Mars introduces a new factor. Autonomy is not optional. When communication is delayed, you must decide locally. So governance evolves. The colony becomes more like a ship at sea than a remote office. But unlike a ship, you can't dock, which means the colony must balance structure with flexibility. And perhaps, over time, it builds a culture with an unusual virtue: patience. Because Mars rewards patience. Now, let's zoom in again, back to daily life. What does it feel like to live in the colony? Because a colony is not only systems, it is mornings, meals, and ordinary work. Chapter 14. Daily Life. The quiet routine that makes survival possible. Morning begins with checks, not obsessive checks, just the rhythm of living inside a machine. A technician reviews overnight logs. Cabin pressure stable. CO2 scrubbers within limits. Water recycling nominal. Power draw and battery status. External weather report. Winds, dust, temperature. Someone else checks the greenhouse. Leaf condition. Nutrient tank levels. Pump performance. Pests. Ideally, none. Growth rates and harvest plan. Someone checks the workshop. Printer calibration. Spare part inventory. Tools cleaned of dust. Filters replaced. Someone checks medical supplies and crew health. And then the day moves into tasks. Expanding regolith. Shielding. Repairing a rover wheel hub. Installing a new air intake filter on the CO2 processing unit. Running water extraction heaters for a planned batch. Inspecting habitat seals and airlocks. Upgrading software for autonomous cargo haulers. There is exercise too. A colony cannot treat exercise as optional. Exercise is maintenance, like cleaning filters, like calibrating sensors. And in the evening, there is the human layer. Meals shared, a story told, a quiet movie, a music session low volume, respectful of sleep cycles, a small ritual, maybe a greenhouse walk, where people sit among plants and let their minds remember Earth. Because mental health is not a luxury. It is part of the life support. And outside, Mars continues. Wind over dust, cold seeping into everything. Stars sharp in the thin sky. A pale Sunday. A small blue star Earth, sometimes visible, sometimes not. The colony learns to find comfort in small consistencies. The hum of fans, the soft glow of grow lights, the steady schedule. This is how humans endure. Now, we should address a question many people ask when imagining Mars colonization. Why not terraform? Why not change Mars itself? Terraforming is an idea that appears in stories, and it's worth discussing calmly and realistically. Chapter 15. Terraforming Mars. A dream, a timescale, and a reality check. Terraforming means changing a planet's environment to be more Earth-like. For Mars, that usually implies thickening the atmosphere, warming the surface, increasing available liquid water, reducing radiation at the surface, creating breathable air. The challenge is enormous. Mars has low gravity and no strong global magnetic field, meaning atmosphere loss processes are a concern on long timescales. Mars does not currently have enough accessible CO2 in the atmosphere to provide Earth-like pressure, even if released from known reservoirs, depending on estimates. Warming an entire planet is not like heating a room. It is energy on planetary scales. And even if you could thicken the atmosphere, creating breathable oxygen requires massive biological or industrial processes over long periods. Terraforming might be possible in a very distant future with advanced technology, but it is not the plan for the first centuries of Mars living. The first colony will not live on a terraformed planet. It will live in habitats, in domes and tunnels, in pressure vessels and caves. So the colony strategy is not change Mars quickly. It is build Earth-like environments locally, small islands, connected, gradually larger. This is more realistic and strangely more poetic. Instead of rewriting an entire world, humans learn to make small, safe places within it. Now, let's address another key difficulty: Mars entry, descent, and landing. The act of getting heavy cargo safely to the surface. Chapter 16: Landing Heavy Things on Mars, the hardest delivery service. Mars is awkward. It has enough atmosphere to create heat and drag during entry, but not enough atmosphere to slow heavy spacecraft easily with parachutes alone. This makes landing heavy payloads extremely challenging. The colony depends on heavy landings, habitats, power systems, excavators, reactors if used, large life support systems, greenhouse modules. Landing them reliably requires heat shields, aerodynamic control, supersonic retropropulsion using engines while still moving fast, precise navigation to land near the base, dust-tolerant mechanisms, high reliability with minimal chance of catastrophic failure. Why does this matter for the colony? Because a colony grows by shipments. If shipments fail, growth slows. If growth slows, redundancy remains thin. If redundancy remains thin, risk remains high. So Mars colonization is not just about living there. It's about logistics. A calm supply chain across tens of millions of kilometers. Now, we talk about the biggest emotional difficulty. What happens when something goes wrong? Because something will. So the colony designs itself not for perfection, but for graceful failure. Chapter 17: Failure Modes. Designing for the day something breaks. The colony plans for power outages, habitat leaks, fire. Yes, fire can happen in oxygenated habitats, toxic contamination, suit failures, vehicle breakdowns far from base, greenhouse disease outbreaks, water extraction system failures, communication disruptions, and it has protocols. Not dramatic, boring protocols. Boring is good, because boring means practiced. A small leak triggers. Alarm. Locate source. Isolate compartment if needed. Patch. Verify pressure stability. Log and review. A power drop triggers. Shed loads automatically. Preserve life support power. Bring backup sources online. Delay non-essential tasks. Diagnose the cause. Dust. Inverter failure. Battery issue. A greenhouse disease triggers. Quarantine. The grow room. Sterilize equipment. Use backup seed and nutrient stock. Shift diet temporarily to stored food. This is why Mars is hard. You must carry a plan for dozens of failure types, and you must rehearse them. and you must build hardware that makes them survivable. It's like living inside a submarine that must also be a farm, a hospital, a power plant, and a factory on a planet. Now we come to a quieter, deeper question. Why do this at all? If it's so hard, why build a colony? There are many answers, and tonight we can hold them gently. Chapter 18. Why humans might choose Mars anyway. Some reasons are scientific. Mars holds clues to planetary history, climate evolution, and maybe past habitability. A colony supports long-term exploration far beyond what short missions can do. Some reasons are technological. Building a self-sustaining habitat teaches us closed-loop life support, recycling, energy efficiency, and resilient engineering. Those lessons can improve life on Earth. Some reasons are cultural and philosophical. Humans explore, we spread, we adapt. A second home is a form of resilience. Not because Earth is disposable, Earth is precious. But because resilience is a habit, some reasons are simply human. People will want to go. Not everyone, but some. The same way some people sail oceans or winter in Antarctica. A Mars colony is a long-term extension of that impulse. And if done responsibly, it can be a careful experiment in how to live with limits. Because Mars makes limits visible. It teaches that air and water are not background, they are systems. And that lesson can be quietly powerful. Now, let's return to our settlers. We'll follow them through a few seasons of colony development, small scenes that tie the science together. Chapter 19. Scenes from the first years. Scene 1. The first regolith cover. In the first months, the settlers drive a small robotic dozer back and forth. It scoops regolith. It pours it over habitat modules like a slow, careful blanket, not too heavy in one place. Even distribution, avoiding crushing loads. The regolith layer thickens. Radiation exposure rates inside drop. Temperature stability improves. The habitat becomes quieter. The settlers sleep a little better. This is not glamorous, but it is the moment the colony begins to feel less like a tent and more like a home. Scene 2. The first water surprise. The water extraction team drills at a site that orbital data suggested was ice-rich. They heat and condense. At first, the yield is lower than expected. Then they realize the regolith composition is different. More salts, different thermal behavior. They adjust. They add a preheating stage. They change filter materials. Slowly, the yield improves. Mars teaches them a pattern. Models are helpful. Reality is the teacher. Scene 3. The greenhouse smell. Months later, the greenhouse is no longer just equipment. It is a place with smell. A green smell. A damp smell. A smell that belongs to life. Someone sits there during a break. Not working, just sitting. The others understand without comment. Sometimes the most important part of a colony is a room where your brain remembers what it means to be a mammal under trees. Scene 4. The dust storm week. A storm arrives. Not a Hollywood wall of darkness, though those exist in the imagination. In reality, it's a steady thickening of the sky. A muted Sunday. A rise in dust accumulation. Solar panels produce less. The colony shifts to emergency power mode. Non-essential systems go quiet. Work outside is limited. People stay in. They do maintenance, training, and planning. It is boring, and that is good. Because boring means the plan worked. Scene 5. The first big repair. A pump in the CO2 processing line begins to vibrate more than normal. Sensors catch it early. The team disassembles it in the workshop. A bearing is warning dust contamination. Despite filters, they replace it with a spare. Then, they redesign the seal arrangement. They 3D print a new component as part of an improved dust barrier. They install it. Vibration drops. The pump hums smoothly again. This is the colony learning to evolve its own technology. Not invent from scratch. Improve. That's how living systems survive too. Scene 6. The first expansion module. A new cargo landing arrives in the next launch window. It brings another habitat, more power capacity, more greenhouse hardware. The settlers connect it. Pressure test, leak test, airlock cycle, and then a new hallway exists. A small architectural victory, a new space to breathe. A colony grows by adding rooms, one room at a time. Now, as the years pass, the colony becomes something larger than its initial mission. But it will never become easy. Mars remains Mars. So, the final part of our story is a calm inventory. What must be true for a Mars colony to be sustainable? And what risks remain even then? Chapter 20. What hour at a sustainable Mars colony requires, and what still might break. A sustainable colony requires these core capabilities. 1. Reliable power with redundancy. Baseline power that survives dust storms. Storage for peaks and emergencies. Maintenance routines and spare parts. 2. Closed-loop life support. Oxygen generation. CO2 scrubbing and reuse. Humidity and contaminant control. Leak detection and repair. 3. Water independence. Local extraction. High-efficiency recycling. Purification and storage. Freeze-proof plumbing and thermal control. 4. Food production at meaningful scale. Multiple crop systems. Disease control and redundancy. Nutrient supply and recycling. Psychological benefits of greenery. 5. Manufacturing and repair. Workshop capability. Standardized parts. Materials processing from regolith. Quality control and documentation. 6. Medical autonomy. Trauma care. Diagnostics. Dental and surgical capacity. Long-term health monitoring. 7. Governance and culture. Safety rules. Conflict resolution. Education and training. Mental health support. A sense of purpose. Even with all of these, risks remain. Unknown long-term biology in 038G. Radiation exposure across decades. Rare but severe solar events. Supply chain disruptions due to launch failures or politics. Psychological strain from isolation. Compounding failures in tightly coupled systems. This is the central reason Mars colonization is hard. A colony is a set of interlocking loops, and interlocking loops can cascade if neglected. So the colony must become excellent at prevention. not heroics. Prevention, a calm, steady competence. Now we close the story the way we began, quietly, because the most realistic Mars colony is not a loud triumph. It is a continuous act of care. Closing scene, a lighted window on a cold planet. Night on Mars is cold and thin. The landscape is still. Dust lies where it fell. Far above, the moons Phobos and Deimos move quickly, like hurried thoughts. Inside the habitat, there is light, a warm, controlled temperature, a soft hum of fans, a faint scent of plants from the greenhouse corridor. People finish their last checks. They log the day's data. They tighten a panel. They replace a filter. They drink recycled water without thinking much about it, because now it tastes normal. They eat a meal that includes fresh leaves grown under LEDs. Somebody prints a small plastic bracket for tomorrow's repair. Someone else writes a message to Earth that will arrive later, delayed by distance, but still real. And then the colony sleeps. Not because Mars is safe, because the colony has made a small, safe place. A bubble of Earth's habits, built from Mars's materials, maintained by human attention, protected by layers of redundancy. A fragile island in a wide, cold sea. That is what it means to build a colony on Mars. It is not one grand leap. It is 1,000 small decisions that keep life continuous. And it is hard because Mars demands that continuity every hour, every day, every year. But in that difficulty, there is also something quietly beautiful. A reminder that life is not only a condition, life is a practice, a loop kept unbroken, a lighted window on a cold planet. Sweet dreams.